Alright, hello, welcome back. In this video I'm going to be talking about series solutions to first order ODEs. And really this is probably not going to be a super important one of our techniques for first order equations, right? I'm coming back to look at this after we've already been investigating second order ODEs. But I think that this is a good kind of like beginning point for us to go before we go and jump in and look at series solutions to second order differential equations, because those can be a little algebraically intensive and they just like they require a lot of steps. And also, you know, if you know me, if you were in my AP calculus class, you know I really love power series representations of functions. I think it's one of like the best, deepest, most applicable things that I get to show students in my math classes. So you should not be surprised that I would be interested in showing you series solutions to ODEs, right? Now, I'm going to start off with one that we already we know the solution to it, we've known it for a long time, and I'm going to just reconcile this with the series technique and hopefully contrast that in the next video with the second order. I won't be asking you to solve any first order ODEs using series, but I think you could maybe see how if you ran into a particularly bad series, a particularly bad ODE, first order, even if you did, we've got a lot of techniques for first order, right? We've got the integrating factor, we've got a lot of them are separable. There's going to be a lot of things that we can do. We've got them mostly cornered. But say you were actually only interested in maybe a power series representation of a solution to an ODE, which I know physicists and other types of scientists and engineers are interested in, right? So I'm just going to start with an easy one, and that's where y prime was proportional to y, right? We know what the solution to this is. This is y equals c e to the kt. We know that. We've shown it by separation of variables. We've shown it by, hey, here's the thing, check it by taking the derivative. I'm sure there's other ways you could show this too, right? But I'm going to show you this on a series level. Okay? So we're going to suppose there is a solution. And if there is a series solution, then we could probably write if there is a solution, we could write a Taylor series for it. Okay? So suppose y equals the sum as n runs from 0 up to infinity of, I'm not going to put the whole business from last year. I'm just going to say a n x to the n is a solution. Then y prime, one of the things we learned last year is that if we've got a Taylor series, we want to take the derivative of it. Well, a Taylor series is just a big polynomial, and so that would be really easy for us to take the derivative of. We're going to take the derivative term by term. Okay. So what I'm going to do, I'm going to bring down that power. I'm going to reserve judgment on this n for now. N starts somewhere, goes up to infinity, n times a n x to the n minus 1. Okay. Well, if we think about the n equals 0 term here, we had a0 times 1, which was just a0, which was a real number. And when we took the derivative of that real number, it went to 0. So I should still be having a constant term that comes from that a1 times x to the 1. I should have a1 being the very first term. It should be a1 x to the 0. And so look, 1, a1, x to the 0, so n needs to start at 1 here. And that's kind of like one of the big things about what we're doing here with these series solutions. Hold on, something weird happened with my laptop. I'm still recording, life is good. Is the difference here. N equals 0 and n equals 1. And it's going to be an even bigger deal when we go to do second order differential equations, because we're going to not only have this y prime, but we're going to have a y double prime also, okay? And just causing more issues. So ky would be like, well, if I just had a k attached over here. And so if y prime is equal to ky, then y prime minus ky must equal 0, right? So, and then I can write down y prime and minus ky. So that's going to be the sum from n equals 1 up to infinity of y prime is n a n x to the n minus 1 minus k times y, which is the sum as n runs from 0 up to infinity of, hold on, where was it? Oh, it's right there, a n x to the n. And now, okay, what I'm going to need to do is I'm going to need to get the index right and the powers of x right so I can express this as one sum, because this thing does still equal 0. And then what I'll be able to do is I'll be able to make conclusions about the values of a n that will then lead me back to the solution to this. Now, sometimes that does not work, right? We only have a library of, like, you know, if you're in my CalBC class, you have four Maclaurin series that you just know off the top of your head, okay? It'll be very rare that you would actually recognize it, but we can write down the terms of the series for y, and as you hopefully learned last year, if we just know the Taylor series for a function, that's pretty much just as good, especially for a whole bunch of, like, you know, scientific or approximate endeavors like engineering. A high degree Taylor polynomial is going to be just as good as the real thing. Okay, and so hold on, let me think real carefully about what I want to do here before I carry on. Don't want to say the wrong thing, right? All right, I had a visitor and then I had a class come through, so it's actually a little bit later in the day. I'm not exactly sure why I left off, but I think I'm in the place where I need to put these together into one series notation. So the kind of, this one's a little easier. The thing to do is going to be to look at the first term. The first term here is going to have an x to the 0 power, right? And this term also has an x to the 0 power, okay? And so we should be able to get these with one index under one sigma without too much difficulty, right? So what I'm going to do is I'm going to say, okay, my new series is going to start at n equals 0, and it's going to go up to infinity. And what had been 1 is now 0, which makes you think you would need to subtract, but you're actually going to need to add. And just what you want to do is just reconcile with the first term, make sure it's what it's supposed to be, right? So I'm going to say this is n plus 1. That's a n plus 1, x to the n. I'll let you sit with that for a second. Right, I need 1a1 x to the 0. 1a1 x to the 0 when n is equal to 0. Okay, so this is good. And then, you know, I can say minus k times a n x to the n. All right, and then I'm going to, hold on, what am I seeing here? Y prime minus ky equals 0. Right, so I've got all of this, oh, and it's equal to, yeah, it's equal to 0. So I'm going to factor out the x to the n. And I'm going to say that, hold on, this is a formula that's valid for every x, right? And the only way that this can add up to be 0 for every x is if each coefficient is 0. So basically, if this is equal to 0 for every n. So I've got n plus 1, a n plus 1, minus that, minus k a n would be 0. So I could just say it's equal k times a n. Okay, now first of all, one thing I want to point out off to the side is that a n plus 1 over a n, y'all take care, I'll see y'all in a couple days. Yeah, a n plus 1 over a n, well, I could do that. That's going to be, if I divide over here, divide away, that's k divided by n plus 1. Take the limit of that, and that's telling you that this is going to converge, always. Okay. Yeah, provided, that this will converge, at least on some pretty decent interval of convergence. Okay. That was not where it initially headed, but I just saw it ready to happen. So, all right. So what? Let's talk about. what's going on here with these coefficients, this an and an plus 1. Yeah, so let's start like listing out our an values. So I'm going to start with a0. I'm not going to have a formula for a0, so that's just going to be kind of like, well, it's just going to be a constant. It's going to be probably like our c1. Then I've also got the a1, I've got a formula for that. And maybe I'll say an plus 1 equals kan divided by n plus 1. That might be useful. So then I've got a1 is equal to ka0 divided by 2. Hold on, is that right? A1 is, no, that's where I'm plugging in 0. So I've got ka0 divided by 1. A2 is going to be, well, it's an, which was this, times k again divided by n plus 1. So that's going to be k squared a0 divided by 2. A3 is going to be in the same way, k to the 3 times a0 divided by 3 times 2. Okay, I'm going to say that an is equal to k to the n, a to the 0, divided by n factorial. Okay? And so what I've got here is the sum as n runs from 0 to infinity for y is an x to the n, right? So I've got this k to the n times a0 divided by n factorial x to the n. And I don't know, maybe this is just not looking quite right to you. So maybe I'll just rewrite this. I'm going to factor out the a0, because that's just some constant. And I'm going to let n run from 0 up to infinity. I'm going to take the k to the n and the x to the n, and I'm going to call it kx to the n divided by n factorial. And hopefully you recognize that this is a0 times the Maclaurin polynomial for e to the kx. Okay? And so that's where we get it. You know, some number times e to the kt. Whoops. Well, I guess I've been using x all along here, so you know, I guess that is kx, and this is how we come to a solution to a differential equation using a series technique. Okay. Also, suppose we weren't trying to find the name of the function in general. Maybe we were just interested in writing, say, a 5th degree polynomial for it, which, as you hopefully have seen, is good enough in a lot of cases. Well, we could have just gone down to a5, written our polynomial, and moved on with our lives. Okay? That's all I got for you for this video.